So I'm going to discuss the method for solving the differential equation about regular singular point, as I discussed before. That method is known as Frobenius method. In this method, we are having the differential equation, and x equal to x0 is a regular singular point of the differential equation. Then we say there exists at least one series solution of this form. That we are having here y equal to sigma, and it's from 0 to infinity Cn x minus x0 power n plus r. The last in power series method, we having the power was only n. We having adding here r. Here we put the condition that C0 is not equal to 0. Then this constant r, we want to find it, and then we put it here, the value of r, and then we will try to find the series solution. This converges on the interval which contains the value x0. So this is the theorem, and we apply this theorem to solve our problems. Now we have to substitute the values of y here. Also need y dash and y double dash. It means we need to find the derivative of this one. So we expand this equation from 0 to infinity. When I take n equal to 0, I get here c0 x minus x0 n. Then I take c equal to 1, n equal to 1, get c1 x minus x0 n plus 1. Then n equal to 2, I get c2 x minus x0 n minus n plus 2, and so on. And cn, we having cn x minus x0 n plus r. I take the derivative, and we can differentiate term by term. The derivative of this one using power, we'll get here r x minus x0 r minus 1. Here it will be r plus 1 c1 x power r minus n plus 1 minus 1 will be r. Here you get r plus 2 c2 x minus x0, r plus 2 minus 1 will be r plus 1. And the general term, we get here r plus n cn x minus x0, r plus n minus 1. So we take, because we need the second derivative, we take the second derivative of this one. This become here r minus 1 into x minus x0 of r minus 2. Here become here r and get r minus 1. Here get r plus 1, and here we get r, and here we get r plus 1 into r plus n minus r plus n minus 1 cn x minus x0 to power here r minus n plus n minus 1 become minus 2. So we can write this in a general form also. As we have the general form of this one, we have here sigma, and is from 0 to infinity cn x minus x0 to power r plus n. You can see we can just take this term and put summation in this one, and that becomes a summation form. And here I can write this equal to sigma, and is from 0 to infinity. In the last one, we say 1 to infinity, because c0 was constant. We take the derivative in the power series, that becomes 0, and also c1 becomes 0, and the series from 2 to infinity. But here summation will not change from 0 to infinity, because our term here is r minus r plus n into cn x minus x0 to power r plus n minus 1. So if we take here n equal to 0, we get this term, n equal to 2, n equal to 1, we get this term, and so on. So here in this case, we'll get here summation. Again, our summation is not changing. It's from 0 to infinity, because no term is going to be 0 by the derivative. So we get here this term, we take the general term, r plus n into r plus n minus 1 cn x to power r plus n minus 2. So these are my substitution. This is my y dash, and here is my y dash, and this is my y double dash. So when I substitute in my differential equation, I can then find the values of c1, c2, c3, c4 in terms of c0 and c1, and we can write our general solution. As I said, we have to find r before solving it, and we get here, I will explain you this one. We call this equation as indicial equation, and there are two methods of finding indicial equation, one by direct substitution and one by the formula. Inshallah, I will explain you with the help of example. I give the example. We use Frobenius method to solve this differential equation, 2x square y double dash minus xy dash plus x minus 5y equal to 0. Now this first we find the regular singular point. So we can see it here. Our a2 of x is equal to 2x square. This implies that this is 0. X equal to 0 is singular point, because it's 0 at x equal to 0, singular point. Now we find here p of x, or p of x is equal to a1 of x or a2 of x, as here is minus x over 2x square, and that gives me minus 1 upon 2x. So I write here x minus x0, that's x p of x. X p of x is my x into 1 minus 1 over 2x. So we simplify this one, we get minus 1 upon 2. So I find my q of x. My q of x, if I want to find, that's my a0 of x over a2 of x. This is x minus 5 over x square to x square. Now I write here x square, q of x, and this is equal to x square, and we are having here x minus 5 over 2x square, and that give me 1 over 2x minus 5, and these are analytic. If they are analytic, then we say this implies x equal to 0 is a regular singular point. Now we want to find the solution about x equal to 0. So our substitution in this case is step 2. At x equal to 0, we have here y equal to sigma n is from 0 to infinity Cn x to power n plus r. So our x0 is equal to 0. So we can define our y dash. So y dash will be equal to sigma n is from 0 to infinity. We have here n plus r Cn x to power n plus r minus 1. And similarly, we can define y double dash. So my y double dash is equal to sigma n is from 0 to infinity n plus r. Again differentiating it, we get here this n plus r minus 1 Cn x to power n plus r minus 2, where simply we can just use this information we have done. We put here the value of x0 equal to 0. We get n from 0 to infinity Cn x to power r plus n. Here put here this value of x0 equal to 0. We get r plus n Cn, and then x to power r plus n minus 1. Again here we substitute the value of x0. Here we are having a mistake, and this is here x minus x0 to power n plus r minus 2. Now we put here the value of x0 equal to 0. So we get here n and r plus 1 and r plus n minus 1 Cn x to power x0 is equal to 0. So x n plus r minus 2. So we substitute these values in our differential equation, and then we solve it. We substitute the value of y dash and y double dash in our equation. We have 2x square y double dash, that's equal to sigma n is from 0 to infinity n plus r minus 1 Cn x to power n minus r minus 2. Then is minus x into y dash is n is from 0 to infinity n plus r Cn n plus r minus 1. This is my y2. And then x minus 5 into y is n from 0 to infinity Cn x to power n plus r equal to 0. I told you last time when we were discussing the power series that I will always shift the coefficient if it is function of x inside. So here I multiply by x power 2, this x power 2 plus sign, and here is minus sign, they absorb, we get here n plus r. Then I take this x inside, and here n plus r minus 1 multiply by x, they become n plus r. Then here is x minus 5 into this, multiply by x, we get here Cn x to power n plus r plus 1. Multiply minus 5, we keep it outside, and this term is n is from 0 to infinity. We are having here n plus x to power n plus r. Now we observe this one, then we can see here the summation is same. 0 to infinity, 0 to infinity, 0 to infinity, 0 to infinity. We are having the powers. If we look here, if x to power n plus r, here is n plus r, here is n, this is only n plus r plus 1. So it means we want to make some changes here. We put here this n plus r plus 1 is equal to k plus 1. I say I'm taking it because r is not changing, n is changing, and summation of. So we say n plus 1 is equal to k. I will say n equal to 0, then get here k equal to 1. And when n goes to infinity, then k is also going to infinity. If we make the changes in this term, we are getting here this equal to sigma. K is from 1 to infinity. You see n, so what's my n? N is equal to k minus 1. So get here c k minus 1, and then you get here x to power k plus r. So this is the power we get here. I want to change this one to k plus r, and I put here k is equal to n plus 1. So now because we say that these values k or n or m, they are dummy index, so I can change this one, and I say this is my equivalent to, if I take the equivalence, is sigma, then is from 1 to infinity Cn minus 1 x to power n plus r, because I am having here n, so I just want to change this one, because here we say k is dummy, so we can change it to by any value. So we say change it to yk, or we say we put here in the value k is equal to n, so we get this equation. So I rewrite this one, I get here 2 into sigma, n is from 0 to infinity n plus r into n plus r minus 1 Cn x to power n plus r, then minus we have sigma, n is from 0 to infinity n plus r Cn x to power n plus r. So here I replace this term as I just make it equal in the power, and the summation is changed. The summation is from plus, no, this term is changed, sigma, n is from 1 to infinity. I explained you this one. Get Cn minus 1 x to power n plus r minus 5 into sigma, n is from 0 to infinity Cn x to power n plus r, and this is equal to 0. So I have explained this one, so I hope it will be clear to you that how we change this term to this term by equating the powers by n plus r plus 1 to k plus r, and then k was n plus 1, and then we derive this one, and in this way we are having the new equation. That is, here the powers are equal, but summation is not equal. Summation will change. The summation is the third term. The summation is from 1 to infinity. So it means we can make the summation equal by taking n equal to 0 here, from here, and from here, then it will be 1 to infinity. When I take it from this equation n equal to 0 out, what I'll get? I get here 2, I get here r, I get here r minus 1. And we take n equal to 0, this C0, n equal to 0, x to power r. I take n equal to 0 out here, we get here minus. N equal to 0, we get here r, we get C0, x to power r. I take n equal to 0 here out, we get here minus 5, C0, x to power r. Now we have plus sigma. Now this is my summation is from 1 to infinity. My first term will be this one. I take n plus r also common, and we get here 2 into n plus r into n plus r minus 1. Here I'm having here Cn, and I will take Cn also common, and then I have this coefficient minus n plus r, also Cn, and then I'm having here minus 5, also Cn. So I'm having here Cn x to power n plus r. Then one term here is left, we write it again. We're having here plus also, here plus, sigma is out. So we get here Cn minus 1, Cn minus 1, and even I can take this one common, and we can write here this equal to, this I use this one, and this one here is x to power n plus r, and that's equal to 0. All the coefficients are 0. We say I can even take the coefficient x to power r out from here. I take x power r out, so I can write this one as into x plus r, and here x plus r plus n plus r. Now we equate the powers of x to power r, coefficient of this one, both the sides. When I take here x to power r from both the sides, I'll get here C0 I can take out. I can also take this C0 out, and I can just write here the bracket inside. So I have this one. So I just multiply it. I get here 2r square minus r, 2r minus 2r minus r minus 5 is equal to 0, because all the coefficients are equal to 0 on that side. Now we compare the coefficient of x to power n plus r. So that give me here the equation, this one. I get here 2n into n plus r into n plus r minus 1, and then I'm having here minus n plus r. We're having here minus 5 into Cn plus Cn minus 1 is equal to 0, where n here is bigger than 0. N equal to 0 we have taken here, and here the value of n is from 1 to infinity, so we say it's bigger than 0. So we get here these two equations. From this equation we solve it and we get the value of r, and this will give me the recursion relation.